In this video, we are going to take a look at sequences. In particular, we are going to define what a sequence is, take a look at some different types of sequences. We're going to find a general form or the nth term of a sequence, and we're also going to identify some of the terms of a sequence. So let's get started. First of all, what is a sequence? A sequence, very simply, is a list of numbers. So I gave a few examples here. The list of 1, 2, 3, 4, on and on and on and on and on and on is a sequence. 2, 4, 6, 8, 10 is a sequence. 1/2, -1/4, 1/8, -1/16, on and on and on are sequences. So those are all lists of numbers. Now a sequence may be a finite or an infinite sequence. In the examples that I gave here with the dots that followed the numbers, that would imply that they are infinite sequences. And in fact, in calculus, we are concerned with infinite sequences rather than finite sequences. So technically speaking, any list of numbers that goes on infinitely far is a sequence. You could have a computer program randomly generate a sequence of random numbers that goes on and on and on infinitely far, and that would be a sequence. In calculus, what we are generally concerned with are sequences that have some type of a pattern, some type of a sequence where we can find that pattern and do some things with it. All right, so let's talk a little bit about the notation of a sequence. So, the notation of a sequence, a sub 1 refers to the first term of a sequence, a sub 2 is the second term, a sub 3 would be the fourth term, a sub 4, ... on and on and on until we get to a sub n, which we refer to as the nth term of the sequence. So these are a sub 1, a sub 2, a sub 3, a sub 4, on and on are referred to the terms of a sequence. So essentially a sequence is a function, but it's a function where the domain is the set of natural numbers n, and I put W here because once in a while the domain of a sequence will be the set of whole numbers. And remember, the difference between the natural numbers and the whole numbers is simply the number 0. So the natural numbers are the numbers you can count on your fingers. 1, 2, 3, 4, 5, 6, on and on infinitely far. So that's the general domain or inputs of a sequence. The outputs of the sequence would be the terms of the sequence themselves. So let's just see how this is all related here by comparing a function to a sequence. So a typical function would be something like this. We use the function notation f of x, and then 2x plus 3 is what we would call the rule of the function, and x is the input variable of the function. And so this tells us how we get the output variable of the function. Now the domain would be all of the values that we can use for x, and then the outputs would be when we multiply x times 2 plus 3 in this particular case. Well, over here we have a sequence. Instead of f of x, we have a sub n. And so a sub n is the general sequence notation, and so 2n plus 3 would be the rule of the sequence, just like we had a rule of the function. So you can see that there's a very similar look to a sequence and a function as far as the notation goes. Now the difference again is over here with x. X can be any real number. Generally speaking, x can be any real number. That means it could be fractions, it could be decimals, it could be negative numbers, it could be irrational numbers or rational numbers. But with a sequence, remember, the domain n is an element of n, the set of natural numbers. So that means n can only take on the values of 1, 2, 3, 4, 5, etc., etc. All right, a few other notations. Sometimes you will see notation for a sequence that looks something like this. Instead of just a sub n, we have a sub n in the little squiggly brackets. Or sometimes in the squiggly little brackets, and then we have some limiting factors where n is equal to 1 to infinity. It tells us what the values of n are to be. This would tell you that you have an infinite sequence a sub n. So here are some different examples. Now these would be called the general form, or the nth term. We call it the general form of the sequence, or the nth term formula. The nth term formula for a sequence. And so a sub n is equal to 1/2 times 2 to the n minus 1. Using this notation with the little squiggly lines, a sub n is equal to 2n plus 3. And here we have the other type of notation. A sub n is equal to n divided by n plus 1, where n is equal to 1 to infinity. So the most common type of notation is simply the first way, simply writing a sub n is equal to, and then writing the rule of the sequence, which we call the nth term formula. All right. Now, some common types of sequences that you should become familiar with and be able to recognize. The first one is an arithmetic sequence. The general form for an arithmetic sequence is a sub n is equal to a sub 1, that means the first term of the sequence, plus d times n minus 1. Now d represents a common difference, and it's that common difference that distinguishes an arithmetic sequence from other sequences. So let's take a look at some examples to see exactly what we mean by that. So here we have a sequence. A sub n is equal to 2, 4, 6, 8, 10, on and on and on and on. Well, first of all, notice that there is a common difference between each term of the sequence. And we can find that out very easily by simply subtracting any two terms. 4 minus 2 is 2. 6 minus 4 is 2. 8 minus 6 is 2, etc., etc. So the common difference, d, is 2. That means it is arithmetic. The first term of the sequence is also 2. So by plugging those into this little nth term formula, we would get this. A sub n is equal to 2, the first term of the sequence, plus the common difference, 2, times n minus 1. And then algebraically simplifying that, we end up with a sub n is equal to 2n. That would be the general formula for the sequence, or the nth term formula for the sequence. Once we have the nth term formula for the sequence, we can find any term in that sequence. So in some of these examples, I just go through and find the first few terms of the sequence. In other words, a sub 1 is 2. And we get that by simply saying, okay, a sub 1 is equal to 2 times 1, simply letting n be equal to 1. Finding a sub 2 is 4. We get that by saying a sub 2 is equal to 2 times 2, which is 4. A sub 3, we obtain that by taking 2 times 3, which is 6. A sub 4 is equal to 2 times 4, which is 8. And I think you get the idea. A sub 5 is 2 times 5, which is 10. So that's how we can find the terms of a sequence. We start with n equals 1, because remember that the domain, the inputs, the values of n, are natural numbers, starting with 1. Occasionally, it will start with 0, but the sequence will let you know that. So that is an arithmetic sequence. The next common type of sequence that we want to look at is a geometric sequence. And the form of a geometric sequence is a sub n is equal to a sub 1, again, that would be the first term of the sequence, times r, which is the common ratio, to the n minus 1 power. So the common ratio r, first of all, we need to determine if there is a common ratio and what that common ratio is. So the way that we determine if there is a common ratio is by taking any two successive terms and dividing them. So that's what I did over here. I took 1/4, divided it by 1/2. Then I took 1/8 and divided it by 1/4. I took 1/16 and divided it by 1/8. And we could go on and on and on and do that. Well, 1/4 divided by 1/2 is the same as 1/4 times 2 over 1, which is 1/2. And you can see that that's going to be true for all of these ratios. 1/8 divided by 1/4 is 1/8 times 4, which is 1/2. 1 over 16 divided by 1 over 8 is 1 over 16 times 8, which is 1/2. So they all have the common ratio, the ratio of any two successive terms. So with an arithmetic, we have a common difference between any two terms. Okay, there's a common difference between every two terms. With a geometric sequence, we have a common ratio between successive terms. So once we know what the common ratio is, we know what the first term of the sequence is. A sub 1 is 1/2, r is 1/2. We can put that together in the formula that we identified up here. So that's what I did right here. A sub 1 is 1/2. R is 1/2 raised to the n minus 1 power. Now we can check to see if this nth term formula or general formula for the sequence actually works by seeing if we can generate these first 4 terms of the sequence, or actually only did the first 3 terms of this particular sequence. So when n is equal to 1, a sub 1, we get 1/2 times 1/2 to the 1 minus 1 power, which is the 0 power. 1/2 to the 0 power is 1. 1 times 1/2 is 1/2. A sub 2, we have 1/2 to the 1/2 raised to the 2 minus 1 power, or raised to the first power, and 1/2 times 1/2 is 1/4. And likewise, we can see that a sub 3 will be equal to 1 over 8. And those were the first 3 terms of our sequence here. So it looks like our nth term formula works. So that is a geometric sequence. That's another very important type of sequence that we're going to be using throughout this particular unit. And finally, another important sequence that you're going to see from time to time is the, let's use violet, is a recursive sequence. Now, this is not necessarily the general form of a recursive sequence. It's just one way that it might possibly look. And so what this is saying is that a sub n is equal to a sub n minus 1. Now, a sub n minus 1 would be the term that comes immediately before a sub n. A sub n minus 2 would be the term that comes 2 terms before a sub n. And so a recursive sequence is a sequence where each term is dependent on a previous term or terms. So as an example would be this right here. A sub n is equal to 3 times a sub n minus 1. In other words, the nth term of the sequence is equal to 3 times the previous term. That's what this means. any term, the nth term is equal to 3 times a sub n minus 1, or 3 times the previous term. Over here, this is another example. A sub n is equal to 2 times the previous term plus 3 times the term before that. So, as an example, find a sub 1, a sub 2, and a sub 3 for a sub n is equal to 8 times a sub n minus 1 plus 2 if a sub 1 equals 2. Now, one important idea here is that when you're given a recursive sequence, you must be given at least one term in the sequence. In most standard problems, you're going to be given a sub 1. And so if you want to find a sub 1, we were given a sub 1, right? A sub 1 is 2. But now we want to find a sub 2, okay? So a sub 2, according to this formula right here, is 8 times the previous term. So 8 times a sub 1, right? So a sub 2 is equal to 8 times a sub 1, where a sub 1 is 2. That's 16 plus 2 is 18. Well, a sub 3, so a sub 3 is equal to 8 times a sub 2 plus 2. I'm going to write this out up here. A sub 2 was equal to 8 times the previous term, a sub 1, and then another 2. And so a sub 2 is 18. We get that from here. That just goes right into there. And 8 times 18 is 144, plus 2 is 146. And now a sub 4 will be equal to 8 times the previous term, a sub 3, plus 2. Well, 8 times the previous term was 146, so 8 times 146, I guess it was 1168, plus 2 is 1170. And so that's how you work with recursive sequences. Okay, recursive sequences are very important in mathematics. The next thing I want to do here is finding a formula for the nth term of a sequence. Finding a formula for the nth term of a sequence. And so there's some certain strategies that you can use for doing this. First of all, we're given a sub n is equal to 13, 16, 19, 22, on and on and on and on. So what we want to do is look for a pattern. Okay, that's the important thing. My strategy is, let's see if it's arithmetic. If it's not arithmetic, let's see if it's geometric. If it's not geometric, it's difficult to tell if it's recursive or not usually. Then we just have to go to some other strategy. So in this particular case, I notice that there's a common difference between each term. 16 minus 13 is 3. 19 minus 16 is 3. So clearly, this is arithmetic, where d is equal to 3, and the first term is 13. So we just plug that into the general formula for a arithmetic sequence, which again was a sub 1 plus d times n minus 1. And so we get this. And simplifying that, I wrote this kind of out of order. I guess I put this, so that should come first. Okay, so a sub 1 times d times n minus 1, plugging in the 3's and the 13. The first term, I'm not sure what this is. Just ignore that, all right? So the first term is 13 plus 3 times n minus 1, which we can simplify to 3n plus 10. So that would be the nth term formula for the sequence. And so we can find the first few terms of the sequence. And to do that, we simply let n be equal to 1. So a sub 1 is equal to 3 times 1 plus 10 is 13. A sub 2, we let n be equal to 2. 3 times 2 is 6 plus 10 is 16. a sub 3, we let n be equal to 3. 3 times 3 is 9, plus 10 is 19. And we do indeed get the first three terms of this sequence. So we have determined that it is an arithmetic sequence, and we have determined the general or nth term formula for that sequence. In the second problem here, clearly this problem is not arithmetic because there is not a common difference. And even though it's not obvious, there is a common ratio. So always just take 2 or 3 successive terms and try dividing them out. So if you take 98 over 9 and divide it by 14 over 1, evidently you're going to get 7/9. I figured this out before. And if you take 686 over 81 and divide it by or multiply it by the reciprocal, 9 over 89, you're going to get 7 over 9. So there's a common ratio. And again, you can verify that. Once we know there's a common ratio, we know that it's geometric. We can see the first term of the sequence is 14. That just comes from here. And so now we can figure out what the formula is. We know the general form of the arithmetic sequence looks like this: a sub 1 times the common ratio raised to the n minus 1 power, and then plugging in the 14 and the 7/9, we get that formula. We can then find the first few terms of the sequence by letting n be equal to 1. And so we have a sub 1 is 14 times 7/9 to the 0, which is 14. A sub 2 is 14 times 7/9 to the 2 minus 1, or first power, which is 98 over 9. And a sub 3 is 14 times 7/9 to the 3 minus 1, or second power, which is 686 over 81. In the next example, it's getting a little bit more difficult because it's not arithmetic and it's not geometric. Now you can easily see that there is not a common difference, so there's no common d and there's no common ratio. You can verify that. So the strategy that I like to use is to look at the numerator and look at the denominator independently of each other. First of all, the numerator is always 1. So that's pretty easy. The numerator of my nth term formula is just going to be 1. The denominator, I look for its relationship to n. Look for the relationship of each term in the denominator to n. So in this term, this is when n is equal to 1, and yet the denominator is 2. In the second term, this would be when n is equal to 2, but the denominator is equal to 4. The third term is when n is equal to 3, the denominator is 6, and 4 and 8. So what we can easily see is that the denominator is 2 times n. It is twice n. So my nth term formula is going to be 1 over 2n. And you can verify that by simply letting n be equal to 1, and you get 1 over 2 times 1 is 1/2. Let n be equal to 2, you get 1 over 2 times 2, which is 1/4. Let n be equal to 3, you get 1 over 2 times 3, which is 6. That should be a 6. And then, of course, a sub 4 would be 1/8. In the next one, we're going to do the same thing, except it's just a little bit harder. Look at the numerator, look at the denominator independently, and then we also have the fact that there are some negatives in here. So look at the numerator and its relationship to n. So when n is equal to 1, the numerator is 1. When n is equal to 2, the numerator is 4. Disregard the negatives for now. When n is equal to 3, the numerator is 9. When n is equal to 4, the numerator is 16. So it appears that the numerator is n squared. And so my numerator, I'm going to use n squared. The denominator looks like it's 1 more than n. Okay, the denominator is 1 more than n, 1 more than n, 1 more than n, 1 more than n. So my denominator is n plus 1. Now, the only other thing to do is to figure out how we deal with the alternating signs. And we're going to see a lot of this with our sequences and series as alternating signs. And so generally, alternating signs can be dealt with by using a power of -1. Because we know that -1 raised to any odd power will be -1, and -1 raised to any even power, so it raised to an odd power is going to be -1, and -1 raised to an even power will be +1. So -1 raised to a power will either be plus or minus 1, and so that's what gives us the alternating signs. So we want, when n is equal to 2, we want it to be odd. So the even values of n are going to be odd. And so what will do that for us is if we take -1 and raise it to the n plus 1 power. In general, if you want even powers, even terms to be odd, you're going to use -1 to the n plus 1. So as an example, when n is equal to 2, you get 2 plus 1 is 3. -1 to the third power is going to be negative. All right, so this then becomes my nth term. Can I get rid of all that? My nth term is all of this. Just had to check my time here. I only got 4 minutes left. So I think what I'm going to do is save these next 4 problems for another video because I really don't want to run over 30 minutes. All right, hope you enjoyed that.